We can continue to talk about bounds and combining bounds into parent node bounds. We're going to keep in mind the two facts that we had from the previous lecture, which is if we have an upper bound for our subproblems, we can take the maximum of them and find an upper bound to our parent problem. Conversely, if we have a lower bound for both of our subproblems, then we can take the max of these and also find a lower bound for our parent problem. And also, when thinking about upper bounds, we know that if we compute an upper bound for a larger feasible region, that we get a larger value than the upper bound in each of the smaller regions. We're going to combine these facts and consider how we can update bounds a little bit more precisely. A feature of these different properties is that if we were to compute an upper bound for a parent node, we need to know all of the upper bounds of our children node. So for example, if we have this particular parent node and we've computed its current upper bound at 20, and we go to one of its children node, say this node, and compute an upper bound of 13, that doesn't allow us to update the bound at our parent node. That's because the upper bound at our parent node is going to be the maximum of all the upper bounds of the children. And so we need to know all of the upper bounds at all of the children in order to update our parent node. In this case, when we gain that information, namely when we know that the upper bounds are 18 and 13 respectively, we can take the maximum of these upper bounds and update the upper bound at our parent node to be 18, the maximum of the upper bounds at the children node. The situation for lower bounds is very different though. If we're at this same parent node and we've identified a lower bound of 15, and then we go to a child node and identify an upper bound of 17, a better upper bound, then we can immediately update the parent node to be 17. This is again because the lower bounds at the parent node are the maximum of the lower bounds at all the children nodes. But in this case, it works for our favor. If we know we have a lower bound of 17, then we know that we can get at least that value among all the children nodes. And so if this value 17 is larger than our current lower bound, and therefore better, we can immediately update that lower bound. The nature of this difference is based on what counts as a better upper bound and a better lower bound. A better upper bound is a smaller value. And so to find a smaller value when dealing with a max, we need to know all of the terms in the maximization. However, for a lower bound, a better lower bound is a number that's larger. And so if we were to take a maximum of a lot of numbers, we only need to know one of those numbers in order to know that that number is going to be a better value for our lower bound. Now we can stop and ask ourselves the question, what's the point of computing and updating all these bounds? And the objective is really simple. We'd like to look at subproblems and eventually stop exploring them. We can stop exploring a subproblem when we know that either we have an optimal solution or we can't find an optimal solution inside of that subproblem. We call this pruning nodes. A node is going to be pruned when we no longer need to explore that node. There's many different ways to prune nodes, and we've already sort of discussed one of them. We can prune by optimality. If we're in some subproblem and we computed an upper and a lower bound that are equal to each other, we know that we found the optimal solution inside of that subproblem. So we can use all the information that we've had inside of this subproblem to potentially update our bounds. In this case, we've updated our upper bound to 18 and our lower bound to 13. And then stop exploring that node. We no longer need to do any computations associated with the node that has an upper bound and a lower bound of 13. The most interesting case of pruning nodes, though, is pruning a node by bound. Here we have a particular example. We've computed an upper bound at a parent node and a lower bound of this parent node, and we've just completed computing the upper and lower bounds at both children node. We haven't updated any of the bounds yet. When we do update the bounds, we update our lower bound to 19, since 19 is the maximum of 16 and 19, the upper bounds computed in both of the children. We've also updated our lower bound. In this case, our lower bound is 17, the maximum of the lower bounds in all of the children. Now, after updating, we observe a fact. The upper bound of the parent node is 17, or rather the lower bound of the parent node is 17. And so the best feasible solution at the parent node has a value of 17. However, if we look at the child node, it has an upper bound of 16, meaning that there's no feasible solution inside of this child node with a value better than 16. Because the upper bound at this child node is lower than the lower bound at the parent node, which is a lower bound of our optimal solution, we know that the optimal solution can't be in this child node C. Because the optimal solution can't be in this child node C, we can prune it. We no longer need to look in this child node because an optimal solution can't reside there. It's not going to give us any good information about either lower or upper bounds. In some sense, we've already used all the information associated with this node by updating the upper bound and the lower bound at the parent node. So now we no longer have to explore it, and so we get rid of this node. This is called pruning by bound. And this is the most interesting part of branch and bound. We've somehow used the information of various children nodes to say that in this particular node, we no longer need to explore it, despite the fact that we haven't actually found an optimal solution in this child node. The final example of pruning is pruning by infeasibility. In this case, we have a child node and we haven't found any feasible solution, or we have some certificate that no feasible solution exists. In this case, we no longer need to explore this node because this part of the feasible region actually isn't any feasible region. So we no longer need to look at it.